Okay, this is a recording of Chapter 1, Section 2B notes. So we're going to start out with graphing a absolute value function. We talked in class the other day about when we graph absolute value functions. The difference is whether I'm taking the absolute value of a positive or a negative. So how do we do that when we're talking about something in functional notation? Well, let's just start with a graph of it and see what the picture looks like. Hopefully everybody recognizes the V shape of this graph. The most interesting value of x is -3. And when you plug -3 in, you get 0 out. I've also plugged in these other points, plotted those, and drawn this graph in. Many of you know how to do this. You can take a look at these points if you need to, but hopefully everybody can plug that in and take the absolute value. I don't think that's the difficult part. The key to this particular problem is in calculus. In order to discuss absolute value, we have to understand how it works in its piecewise situation. Remember, in the past, you probably learned if you take the absolute value of a number that is positive, leave it alone. If you take the absolute value of a negative number, make it positive. Well, what does make it positive mean? We're going to remember it like this. If you take the absolute value of a negative number, negate it. That's how we're going to remember it from now on. Take the absolute value of a negative number, negate it. So think about this. The breaking point is always going to be the most interesting value of x. What makes the argument of the absolute value function equal 0? That number is -3. So this absolute value function is going to be treated differently to the left of -3 than it is going to be to the right of -3. You could put the equal to on either one of these, but typically we put it here because the absolute value of 0 is 0. We don't have to negate it. We just put it here. But think about this. Any number that's less than -3, like -4, -5, will produce a negative number inside the absolute value bars. In order to make it positive, we have to negate that number. That means any number that's less than -3, you're going to have to negate what's inside the bars. Here it is. I'm negating what's inside the bars. I have to make sure I distribute that negative sign, however, and this will define the left-hand piece of this piecewise function. Where if I plug a number in that is equal to -3 or to the right of -3, -2, -1, 0, I already get positives in here. I can just eliminate the bars without doing anything to the function. Always write piecewise functions. Left to right is top to bottom. So the left piece, and always write the functional part first. Y equals, then the brace. It is a left-sided brace only, no brace on the right. Negative x minus 3, comma, then the domain. There's the domain for that piece. Then write the second piece, comma, x is greater than or equal to, then the domain. Notice this line would have a slope of down 1 over 1, down 1 over, and down 1 over 1, and would have a y-intercept of -3 if it continued past -3. It's just at -3 it stops. And the absolute value says, I'm tired of being such a negative line. I want to be a positive line. And it changes the slope to a positive 1. And if the slope changes positive 1, it's going to change its y-intercept to +3. So this line right here defines this piece. The domain says when to stop. This line right here defines this piece, and the domain is telling us x is greater than or equal to -3 is the only time it's defined. We have to be able to rewrite absolute value functions as piecewise. Moving on to B. B is a great problem. It's on multiple problems, multiple tests that we've seen this. It's talked about a lot in Chapter 2 because of this look here. Let's just say if we point plot it. If we plug 1 in, we'd get 1 divided by 1 is 1. Plug 2 in, 2 divided by 2 is 1. Plug 3 in, 3 divided by 3 is 1. Plug 4 in, 4 divided by 4 is 1. And I have fixed this in the other PDF that I sent out. Okay? If I plug -1 in, look, the absolute value of -1 is 1 divided by -1 is -1. Absolute value of -2 is -2 divided by -2 is -1. Absolute value of -3 is +3 divided by -3 is negative. These are all -1. So what's happening? This is a horizontal line at -1. and then stops and jumps up to be a horizontal line at positive 1. Notice we have open circle on both of these because we cannot plug 0 into this function. But are we sure it's always this horizontal line? It's always this horizontal line? Maybe we're not so sure of values in between these integer values. Let's define it as a piecewise function. When x is less than 0, because that makes this argument equal 0, in order to make a negative become positive, we have to negate what's inside the absolute value bars. It's negative x over x. The x's cancel to produce a negative 1. But when x is greater than 0, not equal to it because it's not defined at 0, when x is greater than 0, the absolute value of x is just x. We can just get rid of the bars. X divided by x is positive 1. This function is defined to be negative 1 over this domain. It's negative 1 when x is less than 0. And it's positive 1 when x is greater than 0. Remember, piecewise functions, left to right, should be defined top to bottom. The functional part should always come first, comma, then the domain for that piece. Remember, the domain in this particular situation for the entire function is that x cannot equal 0. That's why we don't have an equal to on either one of those. C is very similar. Again, we will see this function again. Notice now, I can point plot this. If I plug 0 in, I get 0 out. If I plug 1 in, I get 0 out. If I plug 2 in, I get 0 out. It looks like it's always 0. But to the left, it's not. If I plug negative 1 in for x, I get negative 1 minus the absolute value of negative 1 is 1. So negative 1 minus 1 is negative 2 divided by 2. I get negative 1 back out. If I plug negative 2 in, I get negative 2 out. Negative 3 in, I get negative 3 out. Well, that's a slant line. So you could point plot this, but it's hard to get a really good grasp of what the entire function is going to look like until you look at it in its piecewise definition. Again, the value of x that makes the argument equal 0 for this absolute value is 0. So to the left of 0 is treated differently than the right of 0. When x is less than 0, I have to negate what's inside the absolute value bars in order to eliminate the absolute value bars. So it's x minus negative x. That becomes plus a positive. 2x over 2 is x. That looks like the line y equals x. It is. It just stops as soon as x goes beyond 0. The value of x goes beyond 0. What happens as x goes beyond 0? When x is greater than or equal to 0, these absolute value bars are meaningless. The absolute value of a positive is positive. We can just get rid of the bars. X minus x is 0, and 0 divided by 2 is 0. That's why we always get 0 right here. Okay? This can be graphed in your graphing calculator using the ABS function in your graphing calculator. If you plug it in, you're going to see this in your calculator, but you're not going to get a really good picture of this part because it's right on the x-axis. That's why we have to define it as a piecewise function. So we know this is actually being graphed, we're just not seeing it in our calculator. Okay? Let's just do some other piecewise functions. When we graph standard piecewise functions, the biggest problem for most students is that they look at this piece here and they say, oh, I cannot plug 1 into this piece. But you have to. You have to plug it in to see where this line starts. But let's just start working left to right. I can plug 1 into this piece, and 3 minus 1 is 2. So when I plug 1 in, I get 2 out. I can plug 0 in and get 3 out. I can plug negative 1 in, minus a negative becomes plus a positive. I get 4 out. I've done this. You can't see the color that well, but I've done this in blue. And I graph this line. The problem is it stops being this line with a negative slope as soon as x becomes larger than 1. This graph says I'm tired of being so negative. I want to be more positive. So now it's going to change to be this line. The biggest mistake is that a lot of students will start with the next integer value and they'll start at this point and just go on. Can't do that. I have to plug 1 in to see if I am starting right where the other graph left off. So, when we go to do this second piece, what I will do is I'll try to color code it. I will also, when I plug this value of 1 into this bottom piece, I list it again, but I put an open circle around it. That tells me it's not defined there, but it's starting there. Now, if that is already filled in, then I leave it. Don't put an open circle around that point. And start from that point, and now plot the rest of your points. Or just count out the slope. Just go up 2 over 1, up 2 over 1, up 2 over 1. And then graph that. So this is the first piece of this piecewise function. That's the second piece. They also want you to compute. They're just checking to make sure that you know that -1 is less than or equal to 1, so it's got to go into this piece. And 3 minus -1 becomes 3 plus 1, or 4. I'm asking you to do it here anyways. Just relist these values, okay? Notice they're having you evaluate at pi. Just checking to make sure that you know that pi is greater than 1 because it's 3.1415. And if you plug that in, you get 2 pi back out. So you're going to have that on your worksheets as well. E. We get a lot of these horizontal line situations. And the reason is we get this jump discontinuity. Remember, if we go back up to example B, that is also what is called a jump discontinuity. In other words, the graph is going along, it stops, and then it jumps before it starts again. And it's actually called a jump discontinuity. In next chapter, we will actually formally call it that. But if we take a look at this particular piecewise, how do we read this? Again, I'm not supposed to plug 5 into the top piece, but I have to. If I plug 5 in, I get 1 out. I'm just going to circle it. As a matter of fact, if I plug 4 in, I get 1 out. 3, I get 1 out. I just plotted a couple points to show that this is always 1. Notice now there is an open circle. Now, I may come along and fill this circle in with the next piece if it's a nice continuous graph. However, this one is not. Because now when I do plug 5 into the function, 0 comes out. Notice I didn't circle it. That's the actual function that comes out of this F machine. If I plug 0 in, 5 comes out. I'll say that again. If I plug 5 in, 0 comes out. If I plug 6 in, 0 comes out. If I plug 7 in, 0 comes out. Notice I box this in red because that's the red portion. On this particular problem, there is no domain restriction, right? It's defined everywhere. It is defined when x equals 5. It's defined to be 0. That's why this is a solid dot. That is an open dot. But it is still a jump discontinuity. This graph is cruising along here at 1 until it hits x equals 5. It has an open circle because it's not defined to be 1 at x equals 5. And then it jumps down to 0, and it's always 0 thereafter. It's a jump discontinuity. Okay, plug 0 in, you get 1 out, 5 in. There's just some numbers here you're plugging in, and they want it written in functional notation. Write down jump discontinuity so we get used to that. Now these are going to get a little bit more complicated. More pieces to the puzzle. I color code as much as I can for you like I would on the board. If it was on the board in class, I would be using colored markers. So I have a blue piece, a red piece, and then this black piece. So it's 3 differently defined functions. We have to recognize that this is an upside down parabola. This is a parabola that opens downward because of this negative sign. But one of the biggest things is I need to plug 1 into this. And I get 3 out, but I circle it. I started out with an open circle right here. Then I plugged in 0 because that's less than 1. I got 4 out. I plugged in -1. I got 3 out because -1 squared is +1. -2 squared is 4, and 4 minus 4 is 0. You can even plug in -3 and get out -5. I ran out of room to list all those, but I plotted them. This is an upside down parabola, but if you don't recognize it, you're not going to know how to connect these. So you have to recognize it's an upside down parabola. Parabola that opens downward. Right now, this is an open circle. 1 actually goes into the second piece of this piecewise function. And when I plug 1 in, I get 3 halves plus 3 halves, or 6 halves, which is 3. I get 3 out. I don't circle it. It's filling in that open circle that was temporarily there. And now I'm just going to use the slope to say go up 3 over 2. Up 3 over 2. At 3, notice, at 3, that would be 9 halves plus 3 halves is 12 halves, or 6. And that's a solid dot. It's a solid dot. Am I going to take off right from where the red piece left off? I don't know. I got to plug 3 in here and see. 3 plus 3 is 6. Yep. So I don't want to start up here. That's a mistake that a lot of students make. They'll look at the next integer value. No. You have to plug 3 in and get 6 out. I just circled it to show that it's not defined by this black piece. It's defined by the red piece. But the black piece of this piecewise function starts right here, and it has a slope of up 1 over 1, up 1 over 1, up 1 over 1. Okay? This is a continuous function because every time one piece of the graph stopped, when the parabola stopped, the red line took off right where the blue parabola stopped. And when the red line stopped, the last piece, the black piece, took off right where the red piece left off. Okay? So keep that in mind. Here they're asking to evaluate some. You may want to look at the evaluation here because 1/2 squared is 1/4. That's 3 3/4. They do give you some fractional values, but I don't think there's anything too difficult about evaluating that. Make sure you're careful and make sure you're practicing it. This is a perfect example of how you got to practice it before you look at the key to see what type of mistakes you'll make. The only way to get better at computation is to practice it. Okay, this is probably the hardest problem in this set. The key to these notes, the key to this problem is I gave you probably the most complicated absolute value situation that I could give you. Actually, there's a couple in the Chapter 0 workbook that are even harder than this. But we probably don't need to get that extensive. Even this I'm not putting on the test. I used to, but you just don't see it on the AP test, okay? But the key is if you can break down this absolute value, you should be able to break down any absolute value situation. The key is we have 3 different, I'll call them critical points. We have 3 different times where this function is going to change. Those 3 points are every value that makes the absolute value argument equal 0. So x equals 0, x equals 1, x equals 3. I put those on a number line just so I can keep track of everything because there's a lot. There's actually 4 parts to this graph. It's going to be a 4-piece piecewise function. Let's just do it piece by piece. When x is less than 0, if I plug in -1 right here, I get a negative inside the absolute value bars. How do I make it positive? Negate it. If I plug -1 in here, I get out -2. How do I make it positive? Negate it. Now, when you negate it, you got to negate every term. That's why it's -x plus 1. If I plug in -1, this is -4. How do I make that negative become positive? Negate it. I have to distribute it. -x plus 3. I can add those 3 x terms together to get -x. Add those together, I get plus 4. That defines the left-hand piece of this piecewise function, which is only when x is less than 0. The second piece is this blue piece, and that's defined between 0 and 1. Now I put the equal to on this piece, but you could have put it here. Either one would be fine on these problems. Likewise with the 1. I decided to not include 1 on this piece. It doesn't matter. It can be defined for the blue part or the black part, but not both. Not both. Otherwise, it's not a function. Think about this. If I plug any number in between 0 and 1, like 1/2, this is positive. I don't need to do anything with this. I can just eliminate the bars. That's why it's just x, not negative x. But if I plug 1/2 in here, I still get a negative. How do I make it positive? Negate what's inside the absolute value bars. Negative x plus 1. I still get a negative in here. Negate what's inside the absolute value bars. Negative x plus 3. Don't forget to distribute the negative to all terms. Now these cancel. I get negative x plus 4. So I still have a negative slope, but it's not as steep. But that is only defined by this part. So let's just talk about how my graph is evolving. I graphed the red piece right here. In other words, I started at my y-intercept of 4. The slope is up 3, back 1, up 3, back 1. And I draw this in red, and then I stop. But notice this piece is going to take off right where this piece left off. Because if I plug 0 into this, I get 4 out. And now I go down 1 over 1. It temporarily has an open circle here because I did not define the blue piece at x equals 1. I defined the black piece at x equals 1. It doesn't matter which one you do, either one. Let's talk about the next piece between 1 and 3, like 2. That's positive. 2 comes in here. That's positive. Oh, but this is still negative. So the first 2, I don't have to change. Okay? The first 2, it's x plus x minus 1. I didn't change anything. I just eliminated the bars. But I have to negate that third piece. That's why it's negative x plus 3. 2x minus x is 1x plus 2. Now I have a positive slope. So there's a big change going on when x equals 1. When x equals 1, this picture is changing from negative slope to a positive slope. But if I plug 1 in, I still get 3 out. If I plug 2 in, I get 4. Okay, 3 in, I get 5. And it's an open circle. Open circle right here. But I still have one more piece to go. If I pick a number to the right of 3, let's say 4. Positive, positive, they're all positive. I can just eliminate the absolute value bars. I don't have to negate what's inside any of these. So I'll eliminate the absolute value bars to get x. Eliminate, eliminate. Add them up. Add the terms. 3x minus 4. That is the right-handmost piece. And it's only defined when x is greater than or equal to 3. Again, the equal to could have went here or here. The equal to could have went here or here. The equal to could have went here or here. But just not both. If it's defined both, I will mark it wrong because it's no longer a function. Okay? And so if we plug 3 into this, remember, this graph left off at 3, 5. It was just an open circle because it's not defined at this 3. But when I plug 3 into here, I get 5 back out. It's taken off right where the black line left off. So that open circle gets filled in. The slope goes up 3 over 1, up 3 over 1. There it is. First piece is in red. Second piece is in blue. Third piece is in black pen. And the last piece is in pencil. Okay? If you can get through one of these, you understand absolute value and how these evolve. And these are cool functions. The one I think that I put on, I'm not even sure if there's one on the worksheet, but what has been on a review before in the past, it comes down, flattens out, and goes back. There's only 3 pieces to it instead of 4. You get a nice horizontal part. You might see one of those later on somewhere. Last example, doing composites. I'm going to go through this pretty quickly because I do think that we should be pretty decent at doing composites at this point. But I will reiterate, and all the work is written here when you come through the notes. The only thing I really need to talk to is the whole machine aspect of this. This defines the two machines. Don't think of this as f of x. Think of this as f input equals input plus 5. Don't think of this as g of x. Think of this as g input equals input squared minus 3. X, when I look at f of g of x, x is being inputted into g. If x gets inputted into g, x squared minus 3 comes out. But now this is the new input into the f machine. And the f machine says input plus 5. This is the new input. Plus 5 is x squared plus 2. Always write it like this as an equation. Composites are functions. So write the functional notation equals b, g of f of x. This could be something completely different, or sometimes we get the same thing back out. Let's see what happens. If I plug x into the f function, the f function says input plus 5, x plus 5 comes out. But now this is the new input into the g function. The g machine says whatever comes in, input squared minus 3. This now is that input. That's the new input in the g function. X plus 5 squared minus 3. Now I want to see you multiply this out because I want to talk about x plus 5 quantity squared because it's the last time I will address it in calculus. An Algebra 1 error would be to make this x squared plus 25. Maybe Algebra 2 you make that mistake. Definitely not in pre-calculus and absolutely not in calculus. Okay? We have to know that a binomial squared is first times first. The outer is 5x, the inner is 5x, that's 10x. And the last times last. You cannot forget the outer and the inner when you're squaring a binomial. Okay? That's a major point deduction just because it's something that should be taken care of by now, for sure. I don't expect everything that happened in all your previous courses to be 100% solidified, but this one here is really important. And then subtract the 3 from it. 25 minus 3 is 22. Write it like this. All right, f of g of 0. Let's just start by doing it here. G of 0, if I plug 0 in, 0 squared is 0 minus 3 is negative 3. The output's negative 3, but that output becomes the new input into my f function. F machine says take input plus 5. Negative 3 plus 5 is positive 2. Always write it like this. And most of the time on the tests and quizzes, I'll write this. You just have to fill in the blank. Okay? G of f of 0. If 0 comes into f, 0 plus 5, 5 comes out. But that 5 now is the input into the g function. 5 squared is 25 minus 3. That's how we get 22. Now, both of these, if you find your composite correctly, you could just plug this into your composite. 0 squared is 0 plus 2 is 2. 0 plus 0 plus 22 is 22. So you don't have to even show this step, but you need to make sure that your composite's done correctly. All right, E, G of 2. If I plug 2 into the g function and then take that new input and replug it into the g function. So 2 comes into g. 2 squared is 4, minus 3 is 1. G of 1, 1 squared is 1, minus 3, that's why we get negative 2. So the output from 2 going into g is the new input that's going right back into the g machine. And then it has a little bit more abstract, f of x. If I take x and plug it into the f function, x plus 5 comes out. If I take x plus 5 and plug it right back into the f function, input plus 5. X plus 5 is x plus 10. Make sure that you always simplify. Okay?